All right, guys, so in today's video, we're going to go over all of the details about how to answer AP exam questions where you have to create or interpret a graph. And this happens a lot with lab-based free response questions, and there's a lot of points to be gained or lost here. So the sample question that we're going to use to go over these 5 tips is, we have a student who's investigating how the length of a simple pendulum affects its period of oscillation. They measure the period of one full swing for several pendulum lengths and record the data. So we have a data table here. We want to create a graph of the data that will produce a linear graph. Based on that linearized graph, describe the mathematical relationship between the period and the length. And then we're going to use our graph to experimentally determine the value of g, the acceleration due to gravity. So one thing I'll note here is this would not be like an entire free response question. This might be one section of a single free response question dealing with just creating this graph and some of the stuff that comes along with it. But we're just going to focus on all of the graph related things. So to start here, the first thing that we want to do is make sure we understand which value is, or which quantity is the independent variable and which is the dependent variable. And that is going to be kind of based on the experimental design. And so if you have an experiment that's being conducted where we are setting the length, or we're setting these certain specific lengths, that is going to be our independent variable. The one that you set is the independent, and then the one that is then being measured based off of the one that you set is the dependent variable. So in this case, the period is the dependent variable and the length is the independent variable. This is going to be helpful for telling you which quantity goes on which axis of your graph, and that is the independent variable goes on your x-axis and the dependent variable goes on the y-axis. So as we are creating our graph here, so like I said, our independent is going to go on the x-axis, our dependent goes on the y-axis. We want to make sure that we label our graph appropriately and we have the units there with the quantity. So notice here I have labeled the length in meters and the period in seconds. We can also title our graph as our y-axis value versus our x-axis value. So we want to make sure that we have those in the right spot. And we also want to make sure, I'll add on here, that when we're plotting points, we create a scale that is appropriate for our graph. So we want to make sure that we're spreading our scale out in a way that is going to make our graph nice and big. It fills up most of that space that you have available, and it's easy to read. So don't make a super tiny scale that's going to like crunch your graph into this very tiny space. Not only is that hard for somebody else to read, it's hard for you to determine the type of relationship that you have between your x and y axis quantities, because some graph shapes can look kind of similar to each other. For example, a linear graph and the graph of the square root of x, they can look really similar if you have your points kind of clustered too close together. We want them nice and spread out so it's easy for somebody else to read, but also so it's easier for you to tell what type of relationship you're actually looking at. So if we were to, for example, create a scale for this graph based off of the data table, I might do something like have 5 little tiny spaces here on my graph be 0.2. So go up by 0.2 on my x-axis. So I have about, we'll count that as 1, 2, 3, 4, 5. So 0.2, 0.4, 0.6, 0.8. And 1, and then on my y-axis, this one's going to be a little tougher here. So we don't want to make a break in our graph because even though it's not actually shown here, if we had a length of 0, we would have a period of 0. So it would make perfect sense to have a point of 0, 0 on our graph. So we don't want to put a break in our graph to get to kind of jump up to 0.9. We want to go from 0 all the way up there. So don't put a break in your graph. So here I might just do 0.2, 0.4, 0.6, 0.8, 1, 0.2, 0.4, 0.6, 0.8, and then here is 2. Okay, so that would be an appropriate scale. It's okay if I don't go like all the way up the length of this because it's still pretty spread out along the x-axis. It doesn't it's not always going to work that it's spread out perfectly along both axes. That is okay. All right, so the next thing that we want to make sure here is that we understand what it means to linearize a graph. So by definition, what that means is like we're taking a graph that is nonlinear, working to understand the relationship between the quantities that we have, and then creating a graph based on that that becomes a linear graph. So I've plotted the points here on this graph, and notice this look, like if you were just looking at this really quickly, you might think, oh, this is a linear graph, no big deal, that's easy. But notice it actually does have a little bit of a curve to it. So I would look at this graph and say, actually, you know what, that has a little bit of a curve. I'm not going to call this a linear graph. We are going to, though, linearize this graph. Okay, so we're going to change it around. We're not going to plot period versus length, but we might do something like, and we'll get into what exactly this is. Maybe it's like period and length squared, or the inverse square of period and length. And we're going to graph those two quantities and it's going to be linear. So I'm going to show you how to actually figure that out and how to linearize a graph. So there are 4 main graph shapes that you want to make sure that you are familiar with in order to help you with this linearizing process. So we want to know what it means to have a linear graph, because if we have a linear graph, that means whatever is on your y-axis is proportional to whatever is on your x-axis. So if you're graphing y versus x in a linear equation, you're going to get a linear graph. If you have a quadratic graph, that means y is proportional to x squared. So there we have this curve to our graph. It's not linear, but we could linearize it by graphing our y quantity versus our x-axis quantity squared. For a graph that has this sort of shape, which this is the graph that we have here with the period and the length, this is a graph where y is proportional to the square root of x. So if we graph our y-axis value versus the square root of x, we're going to get a linear graph. So these proportionalities can be really, really helpful for helping you find the linearized version of your graph. So if we were to kind of go with some physics quantities here, maybe you notice here that your y-axis value is velocity and your x-axis value is time. So if you have v proportional to t, if you graph velocity versus time, you'll get a linear graph. If you have a graph of position and time, that looks like this quadratic graph where position x, not like x-axis x, but position x, is graphed versus time squared, that's going to be your linearized graph. Okay, we'll talk a little bit more about this one in a second here, but let's get to this last one. So this last one here is a graph that tells us that our y-axis value is proportional to 1 over our x-axis value squared, so our inverse square graph. And that you commonly see with force and distance. So with Newton's law of universal gravitation, this graph shape comes up. So this one tells us that our y-axis value is proportional to or I was going to say force. So this tells us, so if we were graphing force versus distance, this would tell us that force is proportional to 1 over distance squared. And if we were to graph force versus 1 over distance squared, that's where we would get that linear graph from. So use your proportionalities to linearize your graphs. And in this case, our graph shows that our y-axis value t is proportional to the square root of our x-axis value L. And let me just show you another way that we could write this that would mean the same thing. We can also write this as t squared is proportional to L. If we square both sides, we're getting the same idea here. So if we were to then create that linearized graph, we would be graphing t squared on our y-axis versus length on our x-axis, and that would give us a linearized version of that graph. All right, so being able to linearize a graph, very important. Being able to create these proportionalities from our graph is going to help us with the linearization process, but also this kind of all hinges on knowing these 4 basic graph shapes and being able to recognize a linear graph or quadratic graph or a square root graph or an inverse square graph. Those are your 4 main shapes that you should be memorizing and know. All right, so tip number 4, we want to know how to figure out what the slope actually means. And in some cases, that can be very, very straightforward. So we know, for example, that if we have a graph of velocity and time, you may already know off the top of your head that the slope of that graph is equal to acceleration. But what if we didn't remember that? How could we figure that out without memorizing for like every individual type of graph what the slope means? To do that, we are going to look at the unit of our slope. So that's one option. Or we're going to look for an equation that matches what is being graphed and rearrange it to provide us this like linearized version and identify the slope. So I'll show you what I mean there with our period and length example. But first, if we are going to do it by the means of figuring out what our unit is, the slope would be equal to the change in my y-axis value over the change in the x-axis value. So my y-axis value, if it's velocity, has a unit of meters per second, and my x-axis value has a unit of seconds. So if I divide meters per second by seconds, I get something that has a unit of meters per second squared. I can recognize that as an acceleration unit and say, okay, I know what my slope is based on this unit. It's acceleration. That does require you, though, to know what the units are for the various quantities, but you should always be writing your units with your quantities, so those should kind of be coming pretty naturally to you at this point. Our other method here is to use equations that we know, okay? So if we have this linearized graph, t squared versus L, I might look for an equation that contains those 2 quantities. And we have this equation that we know for the period of a pendulum, where the period is equal to 2 pi times the square root of L over G. And if I want to kind of reconfigure this to have a better understanding of what my slope is, I want to rearrange this into a formula that has the y equals mx plus b format. So if I know t is on my y-axis and L, so like t, something with t is on my y-axis and L is on the x-axis, I just have to do a little bit of rearranging here. So I would do something like square both sides of this equation because I want to get L out from under the square root and away from g. So t squared equals 4 pi squared times L over g. And I'm going to just separate that out in a slightly different way, where I have 4 pi squared over g times L. So notice here, if you're like, well, how does that fit into the y equals mx plus b format? We have y. We have our x-axis value here. And that means this is where our slope is. So our y-intercept is 0, so no plus b, that's not there, that makes sense. but I have y equals m times x. And so that means if I graph t squared versus length, my slope is going to be equal to 4 pi squared over g. All right, so we're looking for an equation that matches up with the quantities that we're graphing. We're going to rearrange it until we have something that looks like y equals mx plus b, and that is going to help us identify what our slope means, because it may not be readily apparent based on what the unit is if you have something like this, but this is another way that we can do that if configuring the units maybe doesn't necessarily like work as well. All right, so although we could do this with units, because if you notice here, our unit for this slope would be, so 4 pi squared, that does not in and of itself like have a unit to it. But if we have the inverse of g would be meters per second squared. So we have seconds squared over meters. And if we find the unit of our slope for the period squared over L, that would also be seconds squared over meters. But you may look at seconds squared over meters and not immediately identify what that is a unit for, and also you'd be missing out on the 4 pi squared part. All right, so that is how we can figure out what our slope means. And then last but not least, we want to be able to not just plot the points. So creating a graph in physics is not about just being able to make a scale, plot points, label your axes. What it's really most helpful for is helping you to identify relationships between quantities, which can help you come up with an equation that will allow you to do things like extrapolate or interpolate to find other data points within that data set. We can describe what the slope means and then use that to do a calculation. We can know what the area under the curve means. So it's almost like kind of reading in another language what a graph is telling you. So for example, if we go back to one of the questions in this sample problem, which was come up with this experimental value for g, if I know that I have t squared is equal to 4 pi squared over g times L. So my slope is equal to 4 pi squared over g. If I calculate the slope of my linearized graph using 2 points that are on the graph, so that would be important. We would always want to choose points that are actually on the graph, or on our trend line, I should say rather. And I come up with the slope, I can calculate that value for g and answer that part of the question. So we want to be able to recognize what features of our graph mean, how we can then translate that into maybe a description of the relationship between quantities or an equation that we can use to do a variety of different calculations.